So I wanted to look at one last example for our applications of sinusoidal models. And the last example is going to deal with what's known as simple harmonic motion. And that is when an object oscillates between two different values. So when we have this kind of oscillating motion, in this case, we have the swing acting like a pendulum, swinging from like the far left over time, swinging to the far right, and then bringing itself back to the far left. So when you have this oscillating behavior, we're going to call this simple harmonic motion. And because we are oscillating between two values, we can model this by a sinusoidal curve. So as we're looking at this swing, we're going to assume, first of all, that as the swing is being moved, it's being pulled backwards 6 feet and let go, and we're going to assume that it's going to keep swinging at a constant rate for a certain amount of time. So for this case, they've locked it in. If you read part B, you can see we're going to lock this in for 10 seconds. So over this time, your friend pulls you back, and you're back 6 feet. And then as time goes on, after 1 second, you're right in that like stationary position. And then you move forward at 2 seconds to 6 feet. And then you're back to that stationary position. And then you go back that 6 feet. So you're swinging back and forth between that. What's going to be weird is that as we model this, we're not going to be able to model a horizontal shift. We're going to be modeling that as a vertical motion because we're going to look at it our distance from a stationary point at 0. So part A wants to know how many seconds does it take to complete one cycle in the motion of the swing. So at 0, we're in the far left position. Then we went 1 second, 2 seconds to the far right. And then after 4 seconds, we're back to that far left position here. So that means that it took 4 seconds to complete one cycle. So that means our period would be 4 seconds. Now, if we want the amplitude, our amplitude value is our value for A. And again, that's half the distance between our maximum and our minimum. So when your friend pulls you back, your minimum here is at 0, because you're at 0 seconds, and you're to the far left 6 feet. So you're at -6 if we think about being pulled away from stationary. And then as time moved on, after 2 seconds, you get to that far right position there. So that's where you would be to the right, 6 feet. Oops, it was 2 seconds, not 0. So if I want my A value, I want to take half the difference between my max and my min value. So if I want the amplitude, I'm going to take that 6 for the far right and that -6 from the far left, and we're going to find half the distance between that. And it shouldn't be a surprise that that's 6 feet since we're moving back 6, forward 6, back 6, and forward 6. So now if we want to maintain that rate and amplitude for 10 seconds, so we're going to keep on that same swing, 6 feet back, 6 feet forward. We're going to keep the same motion continuously for 10 seconds. Let's see how many times we pass through that. So again, at 0, we're at -6, which I'm going to lock down there. And then that same distance I'll lock as 6 feet. My graph is a little bit shifted there. So what I'm going to do is at 0, I'm back at -6. At 1 second, I was at 0. And then at 2 seconds, I'm all the way over at +6. At 3 seconds, I get back to 0. At 4 seconds, I'm down to -6. And we're going to keep repeating this pattern. So that's 4, 5, 6, 7, 8, 9, until we get to 10. All right, so we go again, -6. The next second, we go to 0. The next second, +6, back to 0, down. And so this is what our motion on the swing, if we model that distance away from stationary for that 10 seconds. So they want to know how many times did I pass the resting point of the swing? And the resting point is at 0. So we passed it 1, 2, 3, 4, 5 times. So now what they want us to do is express that arc distance from the resting point of the swing as a function of time. So we're going to use our axis. We're going to let this be t in seconds. And this is our distance that our swing is for our arc, 6 feet back, 6 feet forward, and so forth. So now if I want to write a model, I know I'm going to need my values for A, B, H, and K. So we already have our A value. That's our amplitude that we found in part A. To get my B value, we're going to use that period that we had paper up here. So my B value is going to be 2 pi, because that's a traditional period, divided by the period that we have, which was 4 seconds. So my B value is going to be pi over 2. My K value is the average of my max and min values. So my K value, I'm going to average that 6 and that negative 6. And then now I get to decide what point I want to choose to write my model. So if we wanted to start, again, for a phase shift for cosine, we either start at a minimum or a maximum, and we take the x-coordinate for that point. So in this case, if I chose this guy right here, I have no phase shift because I'm right at 0 for my x value. And since I'm at a minimum, I would use a negative value. So if I'm going to write a cosine model, I might choose this point right here, and I would say, all right, well, that's negative 6 for my negative a cosine. My B value was pi over 2. I had no phase shift, so I'm going to just put x there. I don't need to add or subtract anything, because again, I stayed right at 0 to start the cycle. And then our K value was 0, so I'm not going to put plus or minus anything at the end here. So this would be a nice, perfect model for that. You could have chosen this maximum point, and if you chose that maximum point right there when your time value was at 2, and I want to use this in t, not x. If I chose that as my maximum point and I wanted to write my phase shift for this one, since I'm at 2 seconds, I could write a model and I could say, all right, well, that's y equals, since I'm at a maximum, that would be a positive a value for cosine, because remember, cosine's supposed to start at our maximum. The same pi over 2 for my b, but this time I would put t minus 2, since my shift would be 2 units to the right to start the cycle, and then I would complete that regular cosine. If you wanted to do sine, you have 2 options for how you draw your sine. Since this one's not very difficult because we actually had these points, anytime we would have crossed our axis of wave, that would be a phase shift for sine. And we know we crossed that 5 times, so I could technically write 5 different models based off my graph for my sine model. The other way to find your phase shift for sine is to find the x-coordinate that's halfway between a max and a min. So here my x-coordinate is 0, here it's 2. So if I were to find the average of 0 and 2, it'd be 1. And you can see we're crossing right there at 1. So if I use this as my phase shift for sine, it's going to look pretty similar to my cosine model. I still have that same a value of 6. I'm going to put that sine and that same b value. But this time, since I'm shifting and I'm starting here, 1 unit, again, that's halfway between my max and min, or it's a point right on my axis of wave. I'm going to put that phase shift now as 1. And since my cycle is going increasing and then decreasing, that's a traditional positive sine curve. So I'm going to keep that a positive 6. I could have chosen this guy right here. Halfway between 2 and 4 would have been 3. So again, I would have all of those key values. But since if I'm starting at 3, I go negative, I decrease and then increase for sine. If I dip down and then come back up that valley, then hill, that's a negative sign. So I would need to make my a value a negative to show that reflection took place. So we could keep writing more graphs. We could technically write 1, 2, 3, 4, 5, 6 different models for cosine using any of those max or min points. Or I could write 5 different models using any of those points where I cross the axis of wave to create true equations for this model. I tend to, if I can, stick with cosine if I have a choice, because again, cosine will always work at a maximum or a minimum value. So I would tend to go with that choice. Or if I had to write both a sine and a cosine, I tend to try to pick the points that are closest to my y-axis. So I would probably, if I were to choose, I would have chosen this minimum point because it's right on the y-axis. And then I would choose this point because it's closest to my y-axis right here. And it's a phase shift 1 unit to the right. So that's why I've made my sine as a t minus 1 right there. All right, so that was our last example using simple harmonic motion, where it's just kind of weird because, again, what we're doing is we're taking left and right motion, where we're talking about the distance from 0 that we're swinging, but modeling it as a vertical height over time, but we're still oscillating between those 2 fixed values. I go 6 feet to the left, 6 feet to the right, back to 6 to the left, to the right, to the left, to the right. And so that's how this becomes a sinusoidal curve, even though we're doing a horizontal overlapping pattern.